Welcome back. In the last video we built that Lego model here of our dual electronic Hall effect sensor throttle, and it works quite well. It's a little bit too big, compared to the target dimensions I have in mind, but it's Lego Technic. Anyway, card here, link in the description. Anyway, I told you at the end of last video that this time we would have at least an initial layout for a motherboard, baseboard for our two sensors here to replace that breadboard, which is a little bit unwieldy. And we'll come to that. But before that, we'll have a look at an even smaller model of that. And we will revisit, the friction stuff. You remember at the end of the very first video, I measured the spring pressure, these internal springs here we're using can exert, and I'm a little bit weary of of the results of the values I measured. Card here, link in the description. Enjoy. As I've just mentioned, I built a little non-functional model of my first Lego prototype. And there's a reason for it. You'll see in a second. First of all, that thing helped me visualize. Okay, there's there's our motherboard and the two sensors falling out. It helped me visualize how everything will fit together in the end. You see, these side pieces here, they will exist in the final product. And they're not quite right from the proportions here, so they should be at least at that scale twice as wide. But anyway, the important thing here is that here we have all the mechanics and springs inside, which create the friction here, and at the end here is our magnet for our Hall effect sensor. And besides that, I only have two holes here which are made for screws that will screw into two threaded holes in this central block. So my mechanical parts will just be screwed in here with two screws held to the side, and the screw heads will also serve as stops for my throttle levers. And that's basically all the assembly necessary for screws. And of course, there's more going on inside here, but this is basically just a solid piece of plastic, probably. I'm pretty sure I will make it out of POM in this shape. With a real radius here at the top, two threaded holes at the sides, so a total of 4 threaded holes at the side to attach the mechanical parts, and then a big hole here in the middle, the big dark hole, which will house the electronics. So hermetically sealed after you screw that on a console or whatever. Well, there's a little trick here to get that sealed, and this is, there will be one circular groove here for one big O-ring. So we get, remember, it should all be IP68. So we get here, when we screw that onto something, a real good seal on the bottom. So and the bottom is really the only opening to the electronics. And then we're watertight. And there must be, of course, at least one screw hole to screw that in here and to hold it in place. So there will probably be it's quite dark in there, sorry. There will probably another threaded hole down here, or maybe more than one, to hold the electronics in place. Anyway, there's enough meat up here to, to also have this hole only internally and not break through here to the top. Again, everything keeps being sealed. And my electronics are falling apart here. This part here is help me visualize something or realize something. You know, I have to hold that onto the console or whatever surface it's mounted on with screws. And these little stubs here should visualize the screws. And if you place these stubs here in a way that you can put a circular O-ring around them, then the slot I can mill in here for the electronics is, at the sides, very narrow and spans basically most of the width of my main body. So I need to make the baseboard as narrow as possible at the sides where the sensors are sitting or will be attached. That's an important point to take away from here. Let's move on to the initial layouts. There's not really much to it. We just have to connect our two A1335 breakout boards with the sensors together on a little motherboard. Let's call it motherboard from there on, which has absolutely no components, is just connecting the ground connections and the VCC connections and the I2C, SDA as well as SCL connections of both breakout boards. And then we have here 1, 2, 3, 4 through holes to somehow, attach wires. So we can give the whole thing some power supply and we get our two I2C lines off to where we want it. So probably initially an Arduino, of course. Let's have a look at the first layout I came up with. And that was that ugliness here. And you noticed maybe that it's not really narrow, but more squarish. And that's because in the beginning I was just in my head, not looking at some model or some drawing. I was really of the opinion that I have to minimize the width of my baseboard, my motherboard. And so I squeezed it in that direction here and ended up with some holes. Maybe I could cut that off a little, but I ended up with about 33 millimeters in width. So not very narrow. And but on this side it only has 30 millimeters. So it looked really great. I liked the layout. But then I stumbled about the fact that I need more something like that here. Very narrow and longer. Anyways, let's have a look at the second layout after, giving the whole thing more thought. And here it is. And you see, that's much more that form factor here. So again, here we have our breakouts, our breakout boards with the sensors. A few traces to connect the pins, our 4 through holes to connecting some wires here, and 2 hole mounting holes here, which also can act as a wire relief. I route a cable down, 3-dimensional down here, and I solder it in here, and then I can put some strain relief here, which actually also mounts the whole thing inside my main body with 2 screws. And that's it. The important dimension I got out here is 22 millimeters. So I don't want to have that slot any narrower than 22 millimeters. I could probably, if I route here between the pins, I could probably shave off 2 to 4 millimeters more, but I don't really want to. Yeah. Anyways, let's move on to the next topic, which is friction. Yeah, we talked about most of these things in part 1. I already covered it, link in the description. First, some errata. I said here the radius of my Lego friction wheels is 17 millimeters. But 17 millimeters is actually the diameter. So the radius is 8.5 millimeters. And that would translate to an aluminum axis with a radius of 3.7 millimeters or a diameter of 7.4 millimeters equivalent. Yeah, from the friction. Anyway, I also measured at the end of the first video that the force my Lego spring, my main Lego spring exerts is about 5.9 newtons. And as I mentioned in the intro, I don't trust that. So I want to find another way to measure that force. And we will do that by actually measuring the torque I need to move my levers. Okay, let's do that. Like in part 1, I will use a scale to do that. And the important thing here is that we only measure the force at a 90-degree angle here to the lever. Otherwise, we would have to use trigonometry and measure also the angle the force is applied. So I added here another Lego brick here at one of my lever assemblies, and we will press that down here at the end like that, keeping the angle at 90 degrees if possible, or as close at 90 degrees as possible. But then we introduce another error. Okay, there's a little bit of... you can read it. It's okay. If I put a load here on the scale exactly at the middle, then we see that little USB power brick weighs 69 grams. But if we put that here at the very edge, it also comes to 69 grams. You have to verify that. The mechanics inside the scale might be a little too weak to compensate for that offset of force and give you a false reading. But obviously that's not the case. So let's try that here. Okay, 70 grams, and okay, that's our notch. So between 50 and 70 grams, let's try that again. Yeah, 75 notch on the other side. Yeah, let's say between 65 and 75. One more time. The notch doesn't count. Yeah, let's say between 60 and 75. The length of our lever is about 9 centimeters or 0.09 meters. Okay. And the maximum force we measured was 75 grams, or the weight was 75 grams or 0.075 kilograms. and we multiply that by the acceleration in the Earth gravitational field, 9.81 Newton per kilogram, and we get to a force that was actually exerted here of just 0.74 Newton. And with the length of the lever, remember the torque is equal to the radius times the force, we get to a torque of 0.09 times 0.74 equals 0.067 Newton meters. I already mentioned that the diameter, the radius here of our friction wheel is 8.5 millimeters, so 0.0085 meters. And if we calculate the force that's exerted here, then we come to our, take our moment and divide it by the radius, so our 0.067 Newton meters divided by 0.0085 meters, and we come to a force exacted here in the vertical of 7.9 newtons. Now that's our friction force here, at the right angle of the radius of our friction wheel. Now we have to calculate the spring pressure or normal force, spring force or normal force. And that's basically here the normal force is equal to our friction force divided by our micro, our friction coefficient, which is for ABS between 0.11 and 0.46. And if we do that here, then we get a normal force or a spring force of 7.9 newtons divided by 0.11, so the lower micro here, and that gets us to 72 newtons spring force. Or if we take micro 0.46, then we get 7.9 Newton divided by 0.46 equals to 17 Newton spring force. And that's quite different. It's a big range because the micro is has a wide range for ABS plastic, like it's used for Lego, but it's still way off what I measured as a actual spring force for the spring here of 5.9 Newton. And the reason that's wrong lies in the construction here. So I measured the force of that spring when it's fully compressed. The thing is, I think, because that's not moving here anymore, sorry, I think that's more than fully compressed, and what I get here, the force I get here, is really some bending force from the Lego bricks. Because if you watch here, if I just snap in here the whole thing, can you see that gap here? Come on, snap in. Yeah, this gap opens up. So there is a lot of tension here in the Lego bricks, and that's not spring tension, that's just the flexibility of the ABS material. And so it was a good thing that I redid that measurement here, that very important measurement regarding the friction, in another way. That's it for today. Unfortunately, I'm still quite pressed for time, and so the videos are a little bit shorter than they were a few months ago. But this will probably be over maybe in the fourth quarter. We will see. Anyway, you might have noticed that I also show you some pitfalls I fell into during the development. That's not something I did in my previous project videos, but I thought it might be interesting for you to see that I not come up with, the solution right away, but it's trial and error. Not only trial and error, but also making errors and then going a step back and redoing things. Anyway, till next time, we will see what I will show you then. Bye.